Okay, any questions about last class? So you can ask me questions later if it comes to your mind. But so what we did last time was to talk about last few classes about that's not really a straight line, about a pressure temperature phase diagram, which looks something like there is a solid liquid line which is very steep with a positive slope. There is a liquid vapor line which is somewhat steep, and there is a solid vapor line which is also somewhat steep. So this over here is the solid, this over here is the liquid, this over here is the gas phase. And this in the middle is solid plus gas, this is liquid plus gas, and this is solid plus liquid. So those are our coexistence regions. By the way, this reminds me of an interesting aside that I like to mention anytime I teach this class. So this is like a map, right? And you can think of solid and gas and liquid as being different countries or different states. So you can think of an abstract map. Again, this has nothing to do with thermodynamics. This is quite early in the morning and it's rainy, so something that some of you might find exciting. Let's say there is a map made up of many countries with boundaries like this. This map could be countries, this could be some sort of chemicals that you have found, some grains or crystal orientations or something like that. And I want you to color this map in such a way that when you color a map, how do you want it to look like? You want it to look like at a boundary, any two countries or any two grains that are next to each other. Again, this has nothing to do with thermo. This is just for your interest. Any two countries that share a boundary should have two different colors, right? So let me ask you a question. Given a map with an arbitrary number of countries, let's imagine some complicated map, where the countries look like this. I don't know, something as complicated as you can imagine. What is the maximum number of colors you need to color any map? Does anyone know the answer? No one knows the answer? I'm surprised. Someone wrote. 4. Why, Caitlin? Or Anthony? Anyone wants to answer? Why 4? Why not 5? Why not 3? Why is 4 is correct, by the way? Yes, that's correct, Anthony. This is called the 4-color theorem in computer science. It is a conjecture someone made hundreds of years ago, I think, that any map can be colored with 4 colors. And it was a conjecture. There was no proof for it until mid 1990s. Then the proof involved using a supercomputer or computer in order to do it. And the full proof is around 1,000 pages long. So if you can prove this, that any map can be colored in maximum 4 colors, you will win the Fields Medal. No questions asked, or you will be very, very famous. So it's an interesting aside, which has nothing to do with thermo. Okay. With that, let's get back to our thermo. So you can go and look up the proof. I know the proof exists, but I have never been able to understand because it is literally 1,000 pages long and it involves a lot of use of computer. So this point in the middle is called the triple point. This is the point at which solid, liquid, and gas coexist, all of them. It's a very, very special pressure and temperature. And at this point, all of you should hopefully also remember that the solid liquid line for water looks something like this. It has a negative slope. And this is true for almost everything else. So the triple point, we have some idea why it exists. We can think of the triple point in terms of the Gibbs phase rule. And for a one component system, we can see that if we have 3 phases, then the number of degrees of freedom is equal to 0. Clearly, if you had a quadruple point, because we know that solid for water, for example, can exist in many, many different phases. So you might ask, well, how about having a quadruple point? Why do you stop at a triple point? So we can see using the Gibbs phase rule that if for a one component system, if we had 4 phases, then we would be in trouble. Number of degrees of freedom would be -1. Someone asked me on Slack whether there is a physical explanation for this. I don't know who it was. I'm still thinking. Now, whether an explanation is a physical explanation or a mathematical explanation, that's a question of state. I would like to say this is a physical explanation, but I'm trying to think if there is something even more intuitive than the Gibbs phase rule to explain this, that you cannot have a quadruple point for a single component system in a pressure temperature phase diagram. You could have other axes in this phase diagram. For example, you could vary the composition. Then you have additional degrees of freedom. In that case, you could indeed have a quadruple point where 4 phases exist at the same point. So, but not in a single component phase diagram. The thing that we haven't talked about so far is something very special that goes at this point. This one is called the critical point. It's a very, very special point at which the surface tension between the liquid and gas disappears. It becomes basically hard to tell whether you have a liquid or you have a gas. Critical point is quite complicated. There have been at least one Nobel Prize given for the study of critical point, and there is a huge amount of work onto how does the heat capacity behave in vicinity of the critical point and this and that. I'm not going to get into all of that. I just want to show you a basic idea of what happens at the critical point. So today we are going to talk about the critical point, and today's class is going to be a slightly short class because after this critical point, I am going to talk about solutions, not exam solutions, but ideal solutions and regular solutions. The reason we are going to do that is because we want to be able to talk about multi-component systems. Currently, we have talked only about one component system, but chemistry doesn't really happen in one component system, right? It happens when many, many species are present. So we need to have some infrastructure in order to be able to deal with multi-component system. So starting next class, we will be talking about ideal solutions followed by regular solutions. And eventually we will come to chemical equilibrium of how these components exist with each other. Today will be relatively short. I just want to talk about critical point. I think we will finish in half an hour today. And and then you can ask me questions. I'm happy to hang out for a while. So let's talk about critical point. So, and then I will write down the key idea here. So as the temperature increases, the surface tension between liquid and gas disappears, and they have the same density. Physically, this is related to phenomenon. It leads to very strange things in terms of scattering of light. It leads to things that have names such as critical opalescence. You scatter light through the sample and it behaves in a very funky manner. All sorts of strange things happen beyond this critical temperature. We're not going to get into critical opalescence, but I will show you why this really happens. So let's understand this through our van der Waals model. Let's understand the critical point through VDW equation of state, van der Waals equation of state, which is a model, right? It won't, as you will see, it won't happen in a ideal gas. Ideal gases won't show you critical point. You need to have interaction between the molecules for critical point to happen. And in fact, a good question for you to ponder over is how would the pressure temperature phase diagram look like if you had an ideal gas? Well, you won't even have solid or liquid, right? It's just going to stay gas. So the fact that you have the solid and liquid and gas phase transitions, the reason phase transitions happen is because you have interactions happening between the material. Most of the times phase transition is a competition between enthalpy or internal energy and entropy. So you need to have some interaction for it to happen. If there was only entropy, you can still have phase transitions, but not in ideal gas. So let's try to understand it through the van der Waals equation of state. So what is our Van der Waals equation of state? It's been a while since you probably saw it, but if you have forgotten what it is, the best way to write down the Van der Waals equation of state is to start with the ideal gas law. You write down P is equal to nRT, right? Because I always forget what's Van der Waals equation of state. And I say, okay, what are the physical assumptions that go into Van der Waals equation of state? First of all, I think that the particles don't have really tiny volume, they have a finite volume. So I say P is equal to nRT by V. This would have been ideal gas, but I subtract out a certain volume B for each particle, right? So I get nRT by V minus NB. Then I say, well, this is not the only thing in Van der Waals gas. We also account for attractive forces between the molecule. In order to do that, we have a negative sign because attractive forces decrease the pressure. You don't want to escape out of the classroom. You don't want to bombard against the walls. You want to kind of hang out together, right? So you have an attractive term. And the other thing to remember is that the attractive forces go as the square of density. So you have n squared by v squared. So this is our Van der Waals equation of state. And if you ever forget, this is the way you should proceed. Always think about ideal gas, think about the finite volume correction, then think about correction for attractive forces, and then recall that this correction goes as square of density. Why square of density? Because there is already a density term over here, if you really think about this. We also had the virial equation of state, which essentially talked about powers of density. Density to the power 1, density to the power 2, and then the virial equation had other higher powers of density. So for now, let's just stick with the Van der Waals equation of state. One of the things we never did with the Van der Waals equation of state is to plot this equation at a given temperature. Let's try to do that today and see how it looks like. So let's say we have our pressure volume curve and we fix a temperature. So we are gonna try to plot a Van der Waals isotherm. How does the pressure volume curve look like for a given temperature? So this is at some temperature. So now at that temperature, let's say we fix the volume of pressure. At any given pressure, if we try to solve the Van der Waals equation to calculate the possible values for volume, how many volumes will you get? So if we solve equation 1 at fixed P and T, how many solutions for V do you expect? Any answers? And why? Any answers on this? Any thoughts? Make a guess. Is it really quadratic? Right line of thinking, Jared and Matt, but is it quadratic? Ah, it's cubic. When you multiply things together, when you try to solve it, it will be P times V minus NB times V square is equal to nRT times V square minus AN square by V minus NV. Do you see? It's cubic in V. It's not quadratic. It's cubic in V. So at a typical pressure, you will have 3 possible points for volume that are allowed. And in general, this curve, if you plot it in Mathematica or Wolfram or MATLAB, whatever you want to do, it will look something like this. So at any given pressure, you will have 3 possible volume solutions, because even though you see V over here, hopefully you can see now, this equation 1 implies it's really cubic in V. It's not just quadratic. It just so happens that this point over here is spurious. This solution is unphysical. The middle solution that you get out of Van der Waals equation is Van der Waals equation of state doesn't really matter. So what do these points mean? I'm going to call this one as gas at very, very high volume, you have a gas, right? What word? Which word? Spurious. 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 It's misleading. It's fake news. Fake news. So most fake news can be considered as a local minima in our models of understanding of the world, and we get stuck in these local minima, but let's not get abstract. So we have a gas phase over here at very, very high volume. Why should it be gas? Because, well, you are very separated from each other. You tend to behave more and more like an ideal gas. At very, very low volume, when you compress it too much, you get a liquid. So Van der Waals equation of state won't really give you a solid phase in this at this temperature. So I'm using it. Remember, I'm trying to describe the critical temperature here, which corresponds to only the liquid and gas boundary. I'm not talking about solid. In the middle, so what's going on? And I'm going to use another color to draw over this, and I will use a thicker pen. So we start from gas and we decrease the volume. We come to this point over here. That point, let's call it as point A. Then in an actual experiment for a carbon dioxide or for some other liquid where you can go from gas to liquid, when you perform this experiment where you compress the gas gradually, you will see that Van der Waals equation of state actually does a good job for the gas part. Then it kinds of fails. The actual equation, the actual curve tends to look something like this. It does not go through this volume pressure up and pressure down. That is spurious, that doesn't matter. It kind of skips this middle part and then it goes up again. So what did I draw over here? This is isotherm from Van der Waal. And this is real isotherm because even Van der Waals is an approximation, and there is a very special reason for why it becomes a straight line. When we go to our solutions and really talk about things later, there is something special about that. This curve actually has equal area below the green line and above the green line. For now, let's not worry about it. All I'm saying is you start at G, you compress it, you get to A, then you come to a point D, which is to the left, and then you again go back to liquid. So this point, the points in the middle, they don't really matter. I would have called them B and C, but I'm not even going to number them because they don't matter. So this is an actual this is an actual isotherm for a real gas. This, however, applies only for T less than Tc. This type of a picture. It will happen only if you are in this part, this part, this part, this part of the phase diagram. If you go beyond the critical point, it won't happen. And that's what we want to see, why it goes on. Why should you take my word for this? You can go and plot this. You can put in a value of temperature and you can start increasing the temperature. You will see that for a wide range of temperatures, it looks something like this. So so this region in the middle is the coexistence region. So notice something interesting happened. In the pressure temperature phase diagram, the liquid gas coexistence was a line, and at any pressure, you could not really tell about what is the volume change that is happening just by looking at that phase diagram. When you convert this pressure temperature phase diagram to a pressure volume type of setup, you can see how it's spread out and you have a coexistence region. So you start from G, which is gas, you come down to A, you are it's only gas till this point. And what happens physically at this point, that little nucleus of liquid starts to form. In classical nucleation theory, which I showed you, the AR square minus BR cube type picture. So small nucleus form, little bubbles of liquid form in the gas, and they don't hold on. Most of the bubbles disappear. Some of the bubbles keep growing, and you find bigger and bigger liquid regions. So you have a competition between these small bubbles and big bubbles. The small bubbles disappear. The big bubbles, if they manage to reach a critical size that we saw in our classical nucleation theory, they become bigger and bigger. And at some point, as you keep decreasing the volume, it becomes easier for these bigger bubbles to grow. And I'm not going to write it down in text here if you are watching the video now. And like last time I said, this video was not even being recorded, and that was tragic. It is being recorded. You can watch it later. So it's really a so I will write it down in just the summary. Until t less than tc, there is competition between liquid and solid, and liquid sorry, no, I don't mean solid, I mean liquid and gas. And liquid bubbles have a barrier that they need to surmount. And where does this barrier, but this pencil is too thick, let's go back. Where does this barrier come from? Remember, we had drawn this plot for delta G, which went something like AR square minus BR cube, right? This was the size of the nucleus. This could be nucleus of a solid, this could be nucleus of a liquid. This here, A, was the surface energy term, right? So until the critical temperature, A is positive. There is a surface energy term that exists, and hence you have a barrier that needs to be overcome. As soon as you go to the critical temperature, A becomes zero. And what does it mean for A to become zero? This same curve now looks like just minus BR cube. It just looks like a curve that just goes down. It's so easy for the liquid to form. That's the physical picture of what's going on over here in terms of the barrier. But let's look at these isotherms as to how do they behave as we increase the temperature. So I'm going to draw the same curve in a bigger plot for a variety of temperatures. So I would like to think that the screen is freezing much less now after my last change, right? I didn't use any, I'm so sorry for all of you that it was constantly changing. I mean, in real world, how many times does it happen that you are looking at someone and they just freeze and you have to smack them? You're like, you froze, start talking again. And it's one of those things that makes Zoom very frustrating if it just starts to freeze. Okay, so let's look at our, I'm gonna draw a mega plot. Because I'm going to squeeze in a lot of curves over here. So this is pressure and volume. And I'm going to draw isotherms at different temperature. And I gave you a sense for why the isotherm looks the way it is by introducing the van der Waals equation. I did a bit of cheating, I would like to call it. I did not really explain to you as to why is this curve part in the middle spurious or fake news, and why do you have a solid line right in the middle. You have to take my word for it for now. But even if you don't, it's okay. But for now, let's just assume that an experimental isotherm looks almost like the van der Waals in the very beginning part, in the very end, but in the middle, it has a solid line. And if you're really interested, you can read about this solid line. It comes from Maxwell's equal area construction. This is advanced. We are not studying about this. Most likely we are not going to do it in Chem 481, but that's where it really comes from. I don't think Atkins talks about it. The book by Macquarie talks about it in chapter number 9 or something. So let's plot our isotherms at different temperature. At low temperatures, much lower than critical temperature, it's going to look something like this. And what I'm going to do is to erase the middle part and just draw how it looks for an experimental curve. So it will become something like this, then go something like this, right? And where did this come from in terms of a van der Waals equation? It's coming from something like this. That's how the van der Waals would do, right? Van der Waals would have a cubic part and the middle part just disappears. So you start from gas and you get to a liquid. So this is at some temperature T, much lower than Tc. Now let's go to a slightly higher temperature. As you go to slightly higher temperature, at same pressure, how do you expect the volume to look like? If you are looking at an isotherm and you keep the same pressure, but you increase the temperature, what should the volume do? Should it go down or go up? Any ideas? I'm going to wait. Up, that's correct. Because, well, volume goes up, right? You can think of it from an ideal gas perspective, PV is equal to nRT. If you increase the temperature at the same pressure, the volume has to go up. And same thing applies from the van der Waals equation of state. So this curve, when you increase the temperature, will move slightly to the right. It will look something like this. As you keep, so here what we have done, we have increased temperature. Let's go to even higher temperature. What will happen is, so, and if you want to look from the van der Waals equation perspective, the well basically in the middle becomes smaller. If you go to an even higher temperature, the curve will look like this. This well has become even smaller. Finally, you will reach a temperature at which this middle part, so the middle part you can see is shrinking. It's almost going down. Finally, at a temperature, you will reach a temperature at which the middle part completely disappears, and the van der Waals equation of state gives you an isotherm that looks like this. You can draw this line, you can join this line where this single region appears, and it will look like a dome. This point over here is our critical temperature. Until this what are we plotting over here? Remember, this was all liquid, right? This corresponded to completely liquid, while this corresponded to completely gas. In the middle over here, we have liquid plus gas coexistence region. So this is liquid and gas coexistence region phase diagram in a pressure volume space. Should there be a well maxima above the line? It doesn't have a maxima. It just starts to look like this. It becomes totally boring. There is nothing. And so at this point, which is called the critical pressure PC, the critical volume VC, and this isotherm corresponds to a temperature TC. This is the critical temperature. So there is this is the point at which the surface energy term A has basically disappeared. There is no surface energy term. And it's just favorable for the liquid to form. You cannot tell the difference. It's spontaneous. You don't have a nucleation and growth. So T more than TC is spontaneous change between from gas to liquid. So now we can actually find out the value of this PC, VC, and TC. So related to what Anthony wrote down, it's not a maxima. This PC, VC, TC are, and what do I mean by R? Is, I'm talking about a point, is an inflection point. What do I mean by inflection point? It is the point at which the first derivative of pressure with respect to volume at temperature has gone to zero, but it's not a maxima. It's where the second derivative, if it was a maxima, the second derivative would have been negative, right? But it's an inflection point. So the second derivative at constant temperature is also zero. So why do I say that? You can look at the, if you look at this line that I drew, the dome, this dome that I drew over here, you can see that the peculiar thing about this dome is that the slope goes up, 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 the slope becomes zero, and then it starts to go down, right? But you are not just doing that, you're also talking about the rate of change of the slope. So if you just looked at the slope over here at this point, the slope became zero at this point. That's why you have pressure by volume at constant temperature is equal to zero. But on top of that, you're also talking about the rate of change of the slope with respect to volume. That should also be equal to zero. This can be solved for van der Waals equation of state, which we wrote down, equation number 1, to obtain the critical volume, critical pressure, and critical temperature for a van der Waals gas. What you obtain is that Vc is equal to 3 times P. It's actually quite small. Pc is equal to A by 27B squared, and Tc is equal to 8A by 27BR. This is practice problem for you. I would like someone to do it and post it on Slack. So this is our critical point. There's a lot that can be said about critical points. In fact, many physical chemistry textbooks like Atkins talk about critical point in the first temperature, which I think in the first chapter, which I think is a terrible idea because it's a complicated concept. I like to introduce it much later because now you have a better appreciation for what happens because you have thought about phase diagrams and this and that. So TC is 8A by 27BR. You're going to solve it. So why should you, I should just remove this, right? And I should leave it for you to figure it out. 8A by 27BR. These are the numbers you can calculate it. This is the critical point for a van der Waals equation of state beyond which, so you can pinpoint if this in the phase diagram between liquid and gas, you can pinpoint the value of this point from your van der Waals equation of state. If you had some other equation of state, you would still do the same thing. And you can look at it mathematically. What is an equation of state? An equation of state is equal to pressure for constant number test system. Pressure as a function of volume and temperature, right? That's how many variables do we have here? 3 variables. 3 variables, pressure, volume, temperature. Now you set another equation, which is partial P by partial V at constant T is equal to 0. And you set a third equation, that partial square P by partial square partial V square at constant T is equal to 0. So you have 3 equations. You can solve 3 equations in 3 variables to get one unique solution. That's, I don't know what happened here. You can get one unique solution, and that is our critical point. That's why in the pressure, volume, temperature phase diagram, you don't get a critical line. You simply cannot get a critical line because you have 3 variables and 3 equations. Maybe there is no solution. That is possible if something went funky. But at best, you will have a point. You won't have a line. So this is our critical point and critical temperature. There is, you can go and look up, like I said, Nobel Prizes have been given for this. It's an important topic. But I just wanted to give you a flavor for what happens at this end point in the phase diagram where the map just stops. Is the critical point, and the key thing to keep in mind here is that the surface energy term disappears. So the coexistence region disappears. You cannot really tell the difference between liquid and gas. You have a gas phase and the liquid just forms on its own. There is nothing that's stopping it. It's barrierless and there is no difference. So that's it for critical point. Next time I'm going to start talking about ideal solutions. Ideal solutions are one where the enthalpy of mixing is 0. We will then move to regular solutions where this enthalpy of mixing is non-zero. And finally, we will talk a little bit about real solutions, which will allow us to bring in the concept of something called activity and activity coefficients, just a roadmap for remaining of the semester. After this, what are we going to do after that? After this, we are going to talk about equilibrium constants in terms of chemical reactions. And after that, there will be just a bit of kinetics and a bit of electrochemistry. This is all applied material for what we are doing. Any questions about anything? Otherwise, we will be ending this class early. About today's class or anything else?
To solve the system, can you hear me? Is my mic working?
I can hear you.
To solve the system up above for the critical point, don't you need some equivalency or value? I was on the last page there. For that P equals P of VT, don't you need a value there to plug into a system of equations and find something like an eigenvalue or solve the matrix? You're going to put it into a matrix?
Well, it will be a matrix. So that is just an equation. You know, you have, where did my pencil go? This is something like PV is equal to PV cube plus PV to the power 4, some equation. This one is yet another equation. This one is yet another equation. So you have three equations. You can write them in a matrix form. You can write them in whatever form you want. But it's just an equation. I'm not talking about the value over here. Does that make sense? I'm just talking about the equation of state. This is my equation of state. On top of that, so what is an equation of state? If you want to think about, let's take an abstract view. In this pressure, volume, temperature space, this three-dimensional space, what does this represent? Can you tell me? How would it look like in this three-dimensional space, the first equation? The question is for you, Liam.
Yeah, so that's going to give you a surface. It doesn't necessarily have a plane.
Exactly. So on a surface, on top of that, you're specifying two other conditions. If you just use this condition on, so this gives you some surface, you know, something that I don't know how to draw surfaces then. This gives you a surface. Now, if you impose this second condition on this surface, what are you going to get? You are going to cut through it, right? When you cut through the surface, you will get some sort of curve, right?
Yeah.
And now you bring in the third equation. So this is a surface, this is a curve, and finally, so this, when I say this is a curve, I mean this plus this is a curve, and finally all three of them together on the curve, you are putting another condition and you get a point. So that's the idea over here. The thermodynamics is all really about figuring out what is the surface. Equilibrium is the existence of this surface. Non-equilibrium is deviation from this surface. That's why non-equilibrium is so hard, because you can be different from this equilibrium surface in so many different ways, right? But thermodynamics tells us that such a surface exists. And on top of that, we are putting additional constraints. We are saying you cut a plane, you get a curve. You put yet another condition, you get a point, and that's our critical point. Hopefully that helps you.
Okay, thanks.
Good. Any other questions?
Yeah, so what are the curves that define the boundaries for the region of the supercritical fluid? Because we have like this critical point, but then anything sort of beyond it, like I would imagine would still be undifferentiable.
This is just one boring curve, like the kind of straight looking line that I drew. You can't tell the difference. That's the thing about the supercritical fluid. You can't tell the difference. It's all just one boring curve. Let's see if I have an example in my book over here.
So it would just exist for any, like for the given component, if the temperature and pressure, if either of them are above the critical point?
Yeah, so let me see an example from the internet if I can find one for you. It looks very boring. No, that's the thing. It looks very boring, but it's very interesting because the phases have disappeared. Something is going on there. Yeah, this is better. Let me screen share from my computer. Do you see my Chrome?
Yep.
Okay, so the one I wanted to show you, this one, for example. So you can see how it looks for something ideal. You can see this gas curve at so T1 is a temperature much lower than a critical temperature. The gas curve is kind of well behaved. This liquid one is very steep. That tends to be quite common. And you have the middle region, and this is the dome that I drew you. As you get to this critical point, you can call it all liquid or all gas. You know the difference. It's the supercritical fluid. There is no difference, and the curve looks like this. And so yeah, it's just one fluid. So this is how it looks like in the full phase diagram. Does that answer your question?
Yes, thank you.
Okay, good. Any more questions?
I have a question that's midterm related, not necessarily content related. So for the figures that we're supposed to provide, it says that that's part of the individual report, like the figure drawn by us. So should we have different figures from the rest of our group members for that?
Yes, very much.
Okay.
It's your own figure, you know, it will be, yeah, it's absolutely. Anything in the report is completely your own. And I posted some examples on Slack for similar figures. I can show you if you go to Slack. Do you see my Slack?
Yeah, and I saw those, which is just why I wanted to check to make sure that
these are all your own creations. You know, one student drew it by hand, and that's fine. One student went to this level and used gears and everything. It's up to you. I mean, it's really, I don't expect it to look completely wonderful, but I don't want it. It should look like a figure. If you just write a bunch of text and save its picture as a JPEG and then say this is a figure, I'm not going to buy that. It should look like a figure.
Okay.
And this is your individual work. The presentation is shared work, but this is your individual work. Any more questions? Now is your time to ask questions. I didn't do office hour this week, so I can replace, because I could just rush ahead with ideal gas and then I would finish more peak than any professor has ever done in any semester, which is maybe good, but I'm not going to do that. No more questions? So in this new homework, there is also one problem is really 3 points. You have to write down two concepts that you are not happy about. You can be vague. You can just write down something like chemical potential, which is still useful to me. I know I need to talk a bit more about chemical potential, but if you can be more precise as to what is it that is not clear to you, then I can really address it carefully. So please use this as an opportunity. Don't rush. Take your time. You should address it at the end of this week. It covers all through the semester. And if you really think there are 3 concepts or 4 concepts that's not clear to you, 5 concepts that are not clear to you, then please go ahead and write all of them. If everything is clear to you, then write about something advanced that you would like to learn about. You know, so use it as an opportunity to directly give me feedback as to what is it that is not clear or what is it that you would like to learn. Okay, so I'm going to finish now. And we will be meeting again on Friday. And next Monday, I will be doing office hours. Okay, so see you everyone.